10-second cycle end warning time. During processing, the screen shows all current cycle times in operation. And also, simultaneously to the machines running, allows you to edit cycle times and functions for the next cycle, so that you can very interactively program the machine. You can see the machine still goes, and times and processes are updated on the screen. And it's done. Certain setup parameters are accessible from the setup portion of the system, which allows you to reset the machine home positions. Of course, they're already homed right now. View change position speed lets you select the position down to a thousandth of an inch and the speed at which to get there for a whole bunch of arbitrary operations, which are then selected from the run screen more or less in real time. And as you edit the parameters, let's say we'll try 7.5 here. The machine moves to that position and lets you possibly adjust in a fine-tuning way. And let's say we like that. We'll go out and the machine resets and we're back. There is a miscellaneous parameters menu which has various parameters for controlling the warm-up cycle, which allows the machine to go through the motions and heat up all the various parts of the machine prior to run to bring them up to temperature so that the dough is cooked the right way. Maximum move speeds, miscellaneous parameters. Well, that's basically it for the software. The computer is controlled with a standard run-of-the-mill IBM clone. Costs $500 to $700. There's a surge suppressor on top of it. The back of the unit has some special connectors and cards to run the stepper controllers. That one silver connector is the start of a harness that goes to the limit switches, which are on each mandrel. For the machine's table rotation system, which must be extremely accurate, that harness also connects an optical sensor that's scrunched in there to allow accuracy to within a few degrees, or actually it's less than a degree. Panel, you can sort of see the LEDs twinkling behind the grill, are 3 Oriental stepper motor controllers that interface to the card, stepper controller card that is in the PC. Those are on very standard slide assemblies controlled by stepper motors underneath. Of OSHA approvable safety starts, takes 2 to run it, so your hands can't be in the machine, and a shut-off. On this prototype, strangely enough, on the left of the machine, because the operator owner is left-handed. There are also some control systems supplied by the machine shop installed for other functions that I'm not really responsible for. This is one of 3 tube tuning machines, the other 2 being there and there. They basically take very roughly cut lengths of tubes, load them down into a central station, where the ends are trimmed to the proper length for tuning and nodal points drilled and brought into an output hopper where they're collected for assembly into wind chimes. Tuning machines are software driven by a similar windowed user-friendly interface to the Econe machine. Itself is housed underneath, out of harm's way, in a very well filtered positive pressure environment. Digital signal processing boards for the analysis of the tube's sound and some control boards are in the PC. Some custom designed input and output driver boards I've assembled here in the front, and I'm using some superior electric serially controlled stepper motor indexer and driver combinations. Stepper motors that adjust how deep the cut goes in. You'll see that when the machine's running. Now all these blue and black cables, tubing actually, run all the pneumatic systems. Most of the motions on the machine are controlled with air, which you can probably hear hissing right now. There's always a leak or two. That's controlled by the computer via, what a rat's nest, via some solenoid activated pneumatic valves. And I'll try to explain what's happening as it happens. First we can turn the motors on. Then we select run. Now we're going to follow just one tube, trying to make it easy since there's more than one thing happening at a time. Okay, we'll follow this tube that just came out of the hopper. It goes down and sits in a pre-station which aligns it so that after its long drop it can be aligned properly for the end cutters to cut material off. And there's a tube before it going, and once it gets out of the way, then our tube goes in, gets aligned by a positioning pin, and an initial amount is trimmed off, a fixed amount is trimmed off. The tube is then struck and analyzed with a microphone striker combination, and a fine-tuning amount is removed from the ends as well as nodal point drilling. The tube is then verified to make sure it's in tune and pulled out via that and put into a unloading hopper for collection and removal. This is the loading hopper pushing the tube down and aligned in what I call the pre-station, which pushes it to a relatively centered position. It can be aligned again with a positioning pin that's attached to one of the stepper controlled spindle assemblies. Initial trimming, the tube is struck, analyzed with a microphone and a digital signal processing board in the computer to pick the frequency out of all the noise that you hear right now. As a matter of fact, me talking is being monitored but ignored, hopefully, by the fast Fourier transform algorithms in the computer. More excitement. As you can see, definitely more than one thing happens at a time. There's the loading hopper, there's the pre-station alignment of that tube sitting right there, and there's the actual tuning going on, and then there's removal and insertion into the unloader hopper. Basically grabs and pushes up tubes. Most of the mechanical parts of the machine were designed by designer Eric Baller, who is currently a professor at MIT. The white hopper assemblies were designed by a man named Al Ward, who's somewhere in the Midwest now. All of the computer control and frequency analysis was designed by me, Mark Bernard. Also designed all of the frequency analysis machine parts, various solenoid strikers assemblies that move out of position when they're not needed and move into position when they are, microphone holders, and nodal roller holders. You can see when the tube is struck and analyzed, it needs to be held gently at very proper points, and it's done via those little rollers. The reason rollers are used is for possible rotation of the tube in case we've hit a non-ideal part of the tube, since the tubes are generally oval. Sometimes we need to rotate them to make them, to give them, to pick up the correct side of the tube to listen to. That's what this stepper-driven roller assembly is right here. Visual is a consideration. Along the bottom base and up near the overhead beam are yellow strips. They're on the other side also. 4 yellow strips that if you press will shut the machine down instantly. They've never been used for a real emergency, but you never know. Those would shut all of the electric motors down and stop all movement and put the machine in a very limp state so that any caught hands or whatever, God forbid, are treated gently after that point. Very similar to the one I just showed you. This is the original machine, much larger. Some additional features to allow for tuning other products besides their standard wind chime products, but basically the same. The middle machine here is for our chime-along product, anything that uses 7/8 tubes. This is an interesting machine because it does 3 things at once. In one station, it's initially finishing a tube, just like in the other machine, while at the same time, it's tuning and labeling and scribing the tube in the center station, and at the same time, it's doing the finishing tuning trim off of the third station. The reason why this was broken up like this is because labeling and scribing can't happen concurrent to trimming, whereas on the other machines, the drilling operation, which is similar to the labeling and scribing operation, can be done concurrently to trimming the tube, since you don't have to rotate it like you do with labeling and scribing.